For our final project, we decided to analyze a connecting rod for a piston. Connecting rod is an engine component that transfers motion from the piston to the crankshaft and functions as a lever arm. Connecting rods are designed to withstand dynamic stresses from combustion and piston movement. The small end of the connecting rod connects to the piston with a piston pin. The piston pin provides a pivot point between the piston and the connecting rod. Spring clips are used to hold the piston pin in place. The large end of the connecting rod connects to the crank pin to provide a pivot point on the crankshaft. Connecting rods are produced as one-piece or two-piece components. For our project, it was decided to use a one-piece connecting rod to more easily analyze the stresses and deflections in the part. This image shows our original design that was analyzed. For all the analyses, we used NX with a 3D tetrahedral mesh and a mesh size of 0.5 millimeters. Additionally, we decided to use AISI 1005 steel, which has the following analyzing properties. The piece for a bearing force of 11,000 newtons, which is represented by the downward arrow in this image, it was found that the maximum displacement was 0.275 millimeters and is shown by the red area within the circle. After analyzing the deflection, we looked at the von Mises elemental stress and found that the maximum stress was about 481 megapascals. Based on the material properties, the factor of safety was found to be 436. We looked at the von Mises nodal stress and found that the maximum stress was about 563 megapascals. The factor of safety was found to be 373. Using the same material properties as mentioned previously, the part was analyzed for a compressive force of 12,000 newtons on the large diameter and 8,000 newtons on the small diameter. This is represented by the opposing arrows in this image. It was found that the maximum displacement was 0.11 millimeters and shown by the red area within the box. After analyzing that deflection, we looked at the von Mises elemental stress and found that the maximum stress was 127 megapascals. The factor of safety was found to be 1,655. We then looked at the von Mises nodal stress and found that the maximum stress was about 164 megapascals. The factor of safety was 1,280. The part was additionally analyzed for a torsion force of 160 newton meters around the large diameter. This is represented by the arrow in this image. It was found that the maximum displacement was 2.75 millimeters and is shown by the red area within the circle. The von Mises stress was analyzed and found that the maximum stress was 629 megapascals. The factor of safety was found to be 334. Then looked at the nodal stress and found that the maximum stress was 657 megapascals and a factor of safety of 320. The part was finally analyzed for a bending force of 1,000 newtons at the end of the large diameter. This is represented by the arrow in this image. It was found that the maximum displacement was 0.5 millimeters and shown by the red area within the circle. The von Mises elemental stress was analyzed and found that the maximum stress was 158 megapascals. The factor of safety was found to be 1,332. The von Mises nodal stress was found to be a maximum stress of 200 megapascals and a factor of safety of 1,052. After fully analyzing the original design, we decided to try and further optimize the connecting rod. We decreased the radius of the lower ring from 50.9 millimeters to 48 millimeters in order to enforce the part. As a way to decrease weight, material was taken out of the part as shown in the Y shape on the connecting rod. Using the same material properties as the original design, the part was analyzed with the same bearing force of 11,000 newtons. It was found that the maximum displacement was 0.097 millimeters, which is significantly reduced from the original 0.275 millimeters. The von Mises elemental stress was found that the maximum stress was 175 megapascals, which is reduced from the original 481 megapascals. The factor of safety then became 1,194. The nodal stress then became 196 megapascals, which made the factor of safety 1,069. The part was reanalyzed for the same torsion force. It was found that the maximum displacement was 2.53 millimeters compared to the original 2.75 millimeters. The von Mises elemental stress was analyzed and found that the maximum stress was about 595 megapascals, which is reduced from the original 629 megapascals. The factor of safety was then found to be 353. The von Mises nodal stress found that the maximum stress was 622 and the factor of safety was reanalyzed for the same compressive forces as the original design, represented by the opposing arrows in this image. It was found that the maximum displacement was 0.037 millimeters, which was significantly reduced from the original displacement. Mises elemental stress found that the maximum stress was about 64 megapascals, which was reduced from 127 megapascals. The factor of safety was then found to be 3,298, which is extremely high. The von Mises nodal stress was found that the maximum stress was about 84 megapascals. The factor of safety was 2,488. Overall, the optimized design performed better in all aspects that were analyzed.